All right, so today we're going to do some modeling with exponential applications. And what that means is we're going to use geometric sequence functions to model real-world scenarios. Let's start with problem number one. And we've got a couple different types, and we're going to go through the different types of problems we can have. So number one says the population of a certain town can be represented by this, you see this exponential function, where x is the number of years since 1980. When they give you a year, you say, okay, that's t equals 0. So 1980 is t is 0, so 1985 would be t is 5. Okay, what is the significance of a in this situation? That means, what does it mean in the real world? So a is the population in 1980. It's the initial value. That's what A is, right? Remember, A has always been our initial value, A1. Okay, it's just like A1. What is the significance of B? Well, B represents growth. Represents growth. Now, when the question is given to you in a percent, and it could represent growth or decay, but if it's given to you in a percent, you need to remember, so with percents, whenever you have that kind of problem, growth is modeled by the equation 1 plus r. And decay, if something is decreasing, is going to be modeled by 1 minus r. All right. So that's the basic equation. Let's go to this problem. The population of Severna Park in 2010 was 37,634 people. So what is that? That's A, according to the Census Bureau. I looked that up. If the population is growing, so we have a growth function, at a rate of 10% per year, write a function that represents the population at any time. So here we go. The population at any time t is equal to the initial population, 37,634, times our growth. Now, what is the growth? Well, our growth, represented by B, is going to be 1 plus R, which is 1 plus 10%. And how do we write a percent? 1 plus 0.10, which equals 1.10. That represents growth. So we put in 1.10 here, and then for any t, any number of years. What's the domain for the model? Well, let's sketch a graph. If I were to draw this put this in my calculator, and you can do that right now, so stop the tape and put this in your calculator, you're going to get a graph that looks like this if you have the correct window, remembering that that's the hard part of these things. So let's talk about what window should you use. Well, I think about what's going on the x, that's the number of years. So let's take 0 to 20, okay, with a scale of 2, so it goes up by 2. And let's take y from 0 to population. Now, the population is starting here at 37,000, and it's going up. So let's take 0 to 100,000 with a scale of 25,000 so that we can see the whole graph. If you put in this window, you'll get this graph. What is the domain of this graph? Well, the domain goes from and including time 0, the initial's time, all the way to infinity. The graph doesn't apply before 2010, okay? Then the range is going to be what? It's going to start at 37,634 and go up from there to positive infinity. So that's the domain and range of this graph. Okay, now let's create a table of the population for the first 5 years. So these are our t values right here, okay? First year, and the population, let's put it in the calculator. So this is how you're going to get these numbers. Y equals, we're just going to put this equation in, 37,634 1.10 O caret X. So I've put the equation in. Now I go to the window, I put in 0 to 20 with a scale of 2, then 0 to 100,000. Yeah, the right number of zeros? Yeah. With a scale of 25,000, and graph it. Now, I'm graphing it because I need to know how the population, what the population values are. Second table. Let's look at the table. We see that it starts at 37,000 and goes up to 41,397. So let's put in our population. This is where you get the values. 41,397. And then at time 2 years, 45,537, 50. The next one is, and I'm just reading this off the table. Okay, you guys just copy it off the table. And 60,610. Remember that 1 is going to represent the year 2011. 2 is going to be 2012, etc., etc. Okay? Because this started in 2010. All right. How do we do a growth rate? The growth rate is pretty simple. Okay, the growth rate between these 2 years is just, let's look at it, it's slope, right? Growth rate, m equals the change in y over the change in x. So that is going to be 45,537 minus this value. So when I get that, I subtract this from this, I get 4140 over 2 minus 1, the change in x, 1 year. So the growth rate between these two is 4140. If I do the same thing here, the growth rate between these is 4554. The growth rate between these is 5009. And the growth rate between these is 5510. So let's determine an average growth rate. Okay? If I'm going to determine an average growth rate, I can take all of these growth rates and divide them by the average growth rate, right? So let's do that. So we take our calculator, and we're going to say 4140 plus 4554 plus 5009 plus 5510. And I have 19,213 divided by 4, and there I have an average growth rate of 4803.25. Now, compare the average growth rate to the given rate of 10%. Well, so what is the growth rate if I take 10%? 10% of 37,634 is 3763.4. So what's happening is that this growth rate is larger than this growth rate. Now, another way to determine growth rate is to take, watch this, average growth rate, or the growth rate over the entire time. So this is the growth rate. Same thing, delta y over delta x. And I have the fifth year, 60,610, minus the initial amount, 37,634, over 5 minus times 0. So when I do the subtractions and the divisions, I get 4,594.2. And that's population is increasing, so that's a positive growth rate. So that's people per year. okay? So depending on how you calculate it, it's going to be slightly different. It's just estimation. Suppose the population is decaying exponentially at a rate of 10% a year. What is the equation? The population at any time t is going to equal 37,634. Now, okay, what is my growth rate if I'm decreasing? Well, the rate, the b value, is going to be 1 minus r. So what is that? That's 1 minus 10%, which equals 0.90%. So that's a decreasing. A decreasing growth rate is less than 1. So that's my general formula for a function at any time t. Okay, so let's go to the back. Okay, looking at this kind of problem. The growth of bacteria populations usually depends on temperatures as well as time. Suppose another study of swimming pool water and the bacteria count is 500 at the start. 500 at the start. Because of the weather, it triples every day. So what does that look like? Well, that looks like 1,500 after the first day, and then 4,500, because it's tripling every time. So 4,500 times 3 is going to be 13,500. And then the fourth day, 40,500, and then 121,500. Write an equation that models the relationship between the bacteria count, the number of bacteria, over days. That is equal to what? The starting value, 500, times 3, triples. When something triples, that's what you do. If it were doubling, what would we put there? A 2. Okay? If it were quadrupling, we'd put a 4. 2, the days, D. The number of days. So now, when we use a calculator to determine the following values, this is what we do. Take your calculator, go to y equals, and say 500 times 3 caret x. And that gives us the equation for any value, any d. So we go to the table, or actually we don't want to go to the table here, do we? Because none of these are really integers. So here's what we are going to do. We go second calc. We're going to calculate. What are we going to do? We're going to calculate the value. So we hit value and it's going to graph it for us. And then what we're going to do is we're going to say, it's going to say x equals, and we're going to plug in whatever value we want, 0.5. Enter. So the answer for I is 866. That's where our bacteria is growing after 0.5 days, a half a day. Let's do it one more time. Second calc, value, and let's look at the next value, 2.5. X is 2.5. We enter it. Oh, wow, we've really grown. 7,794 bacteria now. Okay, so we do the same thing. Go ahead, stop the clock and go ahead and do this. And what you should get is 3419.3. What about -1? This is we're going to call invalid because, why is this invalid? Because -1 is before the start of the growth. Now sometimes it works to see what's happening backwards, going backwards. So you just have to think as if it's relevant or not. But if I put in second calc value and I say -1, what's going to happen? It's going to be invalid. You can't have negative time. All right, so this is also invalid for this situation. All right, so what's the domain of my model? Well, if I look at the graph, okay, I'm looking at the graph. What's the domain of that graph? What's happening on the x-axis? Well, it's going from the start, 0, to infinity. That is the domain. What's the range of the graph? Looking at the graph again, now it's hard to see on this particular graph because of the way we've set the window from the last problem. But we remember that the graph is starting at 500 on the y-axis, okay? Because when you sketch it, it's going up from what? 500. So the graph only exists on the y-axis from 500 to positive infinity. That's the range. Okay, so these are the kind of problems. Please keep these notes handy. You're going to do some classwork now with these kind of problems. So we have a problem here where we have, let's look at the type of problems. Triples. When you have a situation where something triples, doubles, quadruples, okay? Here's what you do when you have exponential growth and decay with a percent. This is where we're going to use 1 plus r or 1 minus r. Sometimes we have to do rate of change, and rate of change is just the change in y or the change in x. Okay? And here we had at the very bottom, we had the type of problem where you have decay. So it's 1 minus r. It's decaying at a rate of 10%. 1 minus 10% is 0.9. Okay? I will see you next week.